In previous videos, we looked at precipitation reactions and acid-base reactions. In this video, we're going to look at a third type of reaction where we can predict the products, and those are gas-forming reactions. Just like the previous two videos, these are double displacement reactions. So in this case, I'm given potassium hydroxide and ammonium chloride, and I want to know what the products are. So just as in the other double displacement reactions, I'm going to see what ions are present in my two reactants. And so potassium hydroxide is composed of potassium and hydroxide ions, and ammonium chloride is composed of ammonium and chloride ions. So just as with the other double displacement reactions, I'm going to swap which cations the anions are paired with. So I'll take my outer pair and my inner pair. So potassium chloride, potassium is +1, chloride is -1, so they'll combine in a 1-to-1 ratio. So my first product is KCl. And then my second product, ammonium is +1, hydroxide is -1. So my product is NH4OH. Now, for precipitation reactions, we'd want to check the solubility rules, and we also want to check the gas-forming rules. In this case, I know that it's a gas-forming reaction, so I'm just going to look at the gas-forming rules, which I have on the next slide. All right, so I will give you the table of solubility rules. I'll also give you the table of the gas-forming reactions. And so what we need to do is look and see if either of our products, which I've written again down here, appear as either an intermediate product or as a gas that is evolved directly. And so I can see that the ammonium hydroxide appears as an intermediate product. And so with all of these intermediate products, what happens is they decompose into a particular gas and water. So these intermediate products are not stable. If you form them as one of your products, this isn't the actual product that's formed. Instead, it's going to decompose. In this case, ammonium hydroxide will decompose into ammonium and water. And so if I go back and look at my... So we have the potassium chloride and the ammonium hydroxide. This doesn't form. And so instead, I need to take my ammonium chloride, or my ammonium hydroxide, and decompose that into ammonia gas and water. So the complete balanced equation for this one is now for the potassium chloride to determine its state, it wasn't in the gas-forming rules, so then I want to look at the solubility rules and see, is it a precipitate, is it a solid, or is it going to be aqueous? And the first rule on the solubility rules is that all common potassium compounds are soluble, so we would say that potassium chloride is aqueous. All right, let's look at one more example. Okay, so I'll do the same thing that I did last time. I'll figure out what ions are present in each one of my reactants. So hydrobromic acid is composed of H+ and Br- ions, and sodium sulfide has Na+ and S2- ions. So I'll combine the H+ with the sulfide, I'll combine the sodium and the bromide, and so my products are NaBr, and then the other product, hydrogen has a +1 charge, sulfide has a -2, so I need 2 hydrogens for every 1 sulfur. So my product is H2S. So now I'll go and I'll look at my solubility rules. All right, and I've rewritten the products down here at the bottom. So NaBr, that doesn't appear anywhere in the table, but the H2S does appear. And so this is not an intermediate product. The H2S itself is just a gas, so it doesn't decompose or anything. The H2S is just a gas. So when I go back to my equation, H2S is a gas, and the NaBr wasn't a gas. I'd go and look at the solubility rules. All common sodium compounds, ionic compounds, are soluble, so sodium bromide is aqueous. It's also important to check and make sure your equations are balanced. So I know what the states are, now I need to check that they're balanced, and I don't believe they are. So in order to balance these, I'm going to need a 2 in front of the NABR and a 2 in front of the HBr. And now I think it's balanced and complete.